Now, let's move to theory number 2 that came and corrected the octet rule, the valence bond theory. The valence bond theory states that the covalent bond in the molecule is resulted from the overlapping of some atomic orbitals in the combined atoms, and the rest of the atomic orbitals which didn't take part in the formation of bonds remains as they were in the free atoms. In addition, this theory depends on two main concepts: overlapped orbitals and hybridized orbitals. Let's start. Look, here the concept of overlapped orbitals. For the covalent bond to be arise between, for example, two atoms, we need two different atoms or two similar atoms to get a molecule of compound or element. But on one condition, each atom has an orbital, atomic orbital that has just one single electron. By overlapping these two orbitals, we can get the covalent bond. Okay, so let's start with this example. In case of hydrogen gas, hydrogen molecule, hydrogen 1s1. It has just one sub-level S, and the orbital here is a spherical. It has a spherical shape, okay, and contains just one single electron. The other atom, the same. Here, by overlapping the two orbitals of one s here and one s here, we can get the covalent bond between two hydrogen atoms, as you can see here. Now, application number 2, hydrogen fluoride molecule. Hydrogen 1s1. It has just one orbital with a spherical shape that contains just one single electron. In case of fluorine, look at the end. 2b5, we have 2bz1. So now an overlapping between 1s1 of hydrogen and 2bz1 of fluorine atoms to get the bond between hydrogen and fluorine atoms to form hydrogen fluoride molecule by overlapping these two orbitals together. That was the concept of overlapping. But what about the hybridization or the hybridized orbitals concept? Look, hybridization means it's the process of overlapping between two different orbitals or more of the same atom, not between different atoms of the same atom, to produce a number of new equivalent orbitals called hybridized orbitals. Look, the conditions here of hybridization. Number 1, it occurs between the orbitals of the same atoms. It occurs between orbitals of close energies like 2s, 2b, 4s, 3d. So inside the same atom, and we have two orbitals close to each other in energy. The number of the hybridized orbitals equals the number of pure orbitals that undergoing hybridization. Say, for example, here the hybridization between 1s and 1b, 1 and 1, so we're gonna get two hybridized orbitals. Their name not S, not B, it's sp, and their shape like this, as you can see here, not a sphere and not dumbbells. So sp, we get 2 sp. S and 2b, we get 3, each one sp power 2. S and 3b, we get 4 sp power 3. In addition, you have to know that the hybridized orbitals, look here, the hybridized orbitals are more protrude than the pure orbitals. So the bond that arises between hybridized orbitals gonna be stronger than that between pure orbitals. Let's continue. So we have a molecule like methane gas, CH4. According to the overlapped orbitals, we have 4 hydrogen atoms with 4 atomic orbitals. Each one contains 1 single electron. It's okay. What about carbon atom? Inside the carbon atom, we need to get 4 equivalent orbitals with 4 single electrons. But look here at the electronic configuration according to Hund. 1s2, 2s2, 2b2. We have just 2 orbitals with 2 single electrons. We need 4 single electrons. So let's do excitation. Now we have 4 single electrons, but one of them inside 2s and the others inside 2b. They are not equivalent. They are not equal in energy even. So we need to make hybridization to get 4 equivalent orbitals, which are similar in everything and equal in energy. After the hybridization here, and this hybridization from the type sp power 3, we get 4 equivalent hybridized orbitals. And to decrease the repulsion force between them, they go apart from each other in space by an angle 109.5 till they reach the minimum repulsion and the maximum stability. So now we are ready, carbon atom, to what each one of them to overlapping with 1s, one from a hydrogen atom. So at the end, we can get the methane molecule. Methane molecule, CH4, the angle between bonds 109.5. The bonds here are very strong because they are between a hybridized orbital and a pure one. Now, the molecular orbiter theory, just to make this topic more general, we're gonna talk about not atomic orbitals, we're gonna talk about molecular orbitals. The molecule is considered as a 1 unit or a big atom with multi-nuclei, in which all the atomic orbitals of the combined atoms are mixed or hybridized, forming molecular orbitals. In addition, here we have another types for the covalent bond according to the overlapping position. So we have sigma and pi and delta. Okay, let's talk about sigma and pi. Sigma bond arises due to the overlapping of 2 atomic orbitals, head to head. And these 2 orbitals either hybridized, or at least one of them hybridized, not between 2 pure orbitals. So as you can see here from this figure, we get here sigma bond due to the overlapping head to head, collinear overlapping. While what about pi bond? Here it is the bond that's formed as a result of the overlapping of 2 atomic orbitals side to side, parallel, collaterally overlap. So look here, we have y orbital and another one. Side to side we can get a pi bond. So after knowing that, you can deduce that the bonds, the type of bonds inside methane molecule, sigma or pi, sigma, because it's between one hybridized and one pure. One hybridized sp3 from the carbon and one s from the hydrogen. So here look, let's go back. Here in case of, in case of methane, we have 4 bonds, covalent bonds from the type sigma, because here we are between and a hybridized one and a pure one.